So, today in this session we are going to learn about optoelectronic junction devices. So, this is photonics. We also study in electronics as photonics. So, here in previous cases we have seen that the elemental semiconductors like silicon and germanium, and in the depletion layer in the p-n junction where depletion layer is formed, the electron hole pairs are created. So, these electron hole pairs are created, and the energy required for creating this in case of silicon was nearly 1.1 electron volt, and for germanium it was 0.3 electron volts. So, the minority charge carriers were created by the energy acquired by thermal motions, thermal energies we say. That is the energy which is in the infrared region. So, now here we design our semiconductor with some alloying that is binary alloys or ternary semiconductors that are, or quaternary semiconductors, in such a way that the forbidden gap, the energy of the forbidden gap lies or matches with the energy available with the visible light. So, here visible light when falls at the junction or in the semiconductor creates an electron hole pair. So, this is what we are going to learn, and let us see how we can achieve this. So, in optoelectronic junction devices, the electron hole pair is created by photon absorption. The band gap Eg matches with the energy carried by photons of visible light. So, you see light, suppose I say this is the visible portion of the light. Here we have 0.7 micrometer or micrometer, the wavelength of red light, and here suppose I say violet, that is 0.4 micrometer, 4000 angstrom, 7000 angstrom. Now, in beyond this region we have infrared, and beyond this region we have ultraviolet, UV rays. So, you see here this and this. So, in electron volt the energy content of this 1.8 electron volt, and this is nearly 3 electron volt. So, in these optoelectronic junction devices, the forbidden gap is slightly greater than 1.8 to 3 electron volt. That means, if my optoelectronic junction device has to work with violet light, then the forbidden gap will have the order of 3 electron volt. Suppose it has to interact with red light, it must have the forbidden gap slightly less than 1.8 electron volt. Suppose it has to be here somewhat yellow or green, suppose yellow or green, then it would have something of the order of 2.1, 2.2 electron volt. So, you see all the devices, optoelectronic devices, for example LED, if I want a red LED, light emitting diode, that is a normal p-n junction, the forbidden gap must be 1.5 electron volt. Suppose I want a blue one is very near to this 3, suppose it is 2.8, blue one is here 2.8 electron volt. That means for that junction, that diode, that LED, the forbidden gap will be this much. So, depending on which type of light we want to interact with the junction diode, we have to select the material, and we have a different class of material to do that. Suppose I want a material which works at this place, that is suppose 3.5 electron volt, that is ultraviolet region. That means what type of material will be required and what will be its use? Suppose I want to make an invisible sensor. You might have seen in some movies, some invisible sensor rays are there, and when you pass through that rays, you interrupt that rays, then an alarm will be switched off. So, that means there is a sensor here, a device whose forbidden gap is 3.5 electron volt, and some diode which is creating some rays with this frequency, this wavelength are coming from one place, and at another location they are being absorbed and detected. So, whenever you interrupt that rays, then that detection will be not taking place, and an alarm will be triggered. That means if we work in this region optoelectronics devices, then we have a variety of devices that can be formed. So, here we will study three basic type of devices which works on this idea that this the forbidden gap should lie in this. Number one is photodetectors, photodiodes that are used in various type of alarms, that is water level indicator, etc., or photocell, next solar cells, and then LEDs. So, let us see first photodetectors. So, now there are basically three types of photonic devices. So, you see those devices where photons here play a key role, photonic devices, or optoelectronic junction device. So, they are same thing. Number one we will study is photodiodes. They are used to detect light detectors, light intensity detectors, etc. They are photodiodes. Next is solar or next is LED, light emitting diode, that is LED, and all of us are familiar with LED lighting system. Third, photovoltaic cell or solar cell, which converts light energy in electrical energy. That is actually the reverse of light emitting diode. It converts electrical energy into light energy. So, there are three types of uses of optoelectronic junction devices. Photodiodes, they are used to detect light detectors, they are generally used as detectors, so we often call it photodetectors. Second, light emitting diode, LED, which is used in electrical energy to convert electrical energy into light energy. Next is photovoltaic cell, solar cells. So, first let us see what are photodiodes. So, now let us see photodiodes. So, they are special purpose diodes, that is PN junction. Diode means PN junction, which has a transparent window so that the photons can reach the junction or the depletion layer and can cause carrier generation, that is electron hole pair. So, in this photodiode, you see this is a normal PN junction. This is a normal PN junction. This is the depletion layer. This is the block diagram. So, the light here has to fall here. So, when the light falls in the depletion layer, electron hole pairs are created. Suppose this electron, this is the electron and this is a hole pair created by this absorbing the photon light. So, there is a potential barrier, you see here high voltage and low potential here. So, the electric field is in this direction. So, in this direction the hole will move here and the electron will be. So, the electron hole pair created. So, what we have to do? The electron hole pair created, by photonic absorption is swapped by the high junction field to constitute a drift current. So, we all know the electron hole pair created here is carried by the junction field due to the drift current. The depletion layer is generally made thin so that the electron hole pair created immediately reach their site. Otherwise, they may recombine. So, before they recombine, they must reach their destination. So, depletion layer has to be made very thin. Now, the depletion layer must be sufficiently, it should be thin and thick also. That means it should be thin so that recombination does not take place, and it should be sufficiently thick so that the quantum efficiency is high. Quantum efficiency means the number of electron hole pair creation, the carrier generation per photon absorbed. So, quantum efficiency should be high, so it should be thick. So, there are three constraints when I design this. Number one, this is actually a block diagram where I am not able to tell you that why there is a transparent window, that is that point. So, I will use another diagram to explain this point. So, you see here, it must have a transparent window, number 1 point. Number 2 point, it should be very thin. The depletion layer should be thin, so that by photonic absorption, you see here any bonds between silicon or some alloying, due to that material, the bond will break up and the electron from the valence band will go to the conduction band. So as a result, this electron hole pair will be created and they will be swapped. So what is that? If it is thin, they can easily be swapped to their respective p and n sides, and it should be sufficiently thick so that here more and more the photons can cause this electron hole pair creation. So now quantum efficiency. So you see, all the photons may not be absorbed and cause a transition from valence band to conduction band. You see, this is the energy valence band and this is my conduction band. Here Eg lies between, in visible range, so that is from 1.8 electron volt to 3 electron volt. So if I am using this photo detector for suppose 2.5, so I will be only keeping it from 2.5. So please, presently I am not writing this. So this is Eg lying between this visible region. So now when the photon falls, here this is h nu amount of energy, then a hole is created, and you see this energy gap, the forbidden gap, is equal to this. So this finally goes to here, and thus electron is here. So this is electron, this is hole. So it absorbs h nu. Now you see here, this is a block diagram. Actual diodes won't be like this. So suppose this actual diode is like this. Suppose it is, there are different. So we have this p type and this type n type. Suppose you see this hole which I am shading it, suppose this is shading, I am shading, this is the block which is n type and this is p. So this is my junction. You see, this junction is not something exposed to light by here. This junction is in the sandwiched between this p type and n type. So here the light is falling at the junction like this. So you see, this p portion must be transparent. That is what I said, a transparent window should be there. So the light should come, this should be transparent one, and then it should reach the junction. So here, very important point. First let us see what's quantum efficiency. We define quantum efficiency as the number of electron hole pairs created or minority carrier creation per photon absorbed. Suppose I say it is 1, that means whatever photons are striking here, they are creating the electron hole pair. Generally this is very less, that is suppose 10%, that means suppose 1000 photons strike here, so only 10%, that is only 100 photons can cause electron pair creation. So three things are required. Number one, this window, this p or n type, whether it is p type, n type, or it may be p type here or maybe n type. So depend on diode to diode. So whatever may be, number one, that there must be a transparent window, means any of the n or p type must be a transparent medium. This should be a transparent thing. Second, the electron hole pair creation, the photon absorption. So second point is the photon absorption should take place in the depletion layer, and the depletion layer width should be so small that before they again recombine, the hole and the electrons again recombine, they must be swapped with the high junction field. And third point is that it should be so much thick that the quantum efficiency should be very good. So, these are the criterias which we must take into account while fabricating a PN junction, that is for a junction diode. Now, let us see, to operate this photodiode, it should be always reverse connected. Please take down this. So, this is our photodiode and this is the P side, this is N side. At the depletion layer, this light falls and electrons will be migrating here and the holes will go like this. So, I am showing only drift motion due to drift charge. Now, this photodiode is always reverse connected. So, this is N. So, here positive and this is P with the negative terminal. And so, if we measure this here current, this is in microammeter current, let us measure it. So, when the light falls here and there is a reverse bias, then we will see the current flows in this external circuit. And the characteristics of a photodiode, let us see IV graph for a photodiode. This is very, very important, photodiode. So, number 1 point, let us write the photodiode is always reverse connected, always reverse connected. Its graph is like this. So, you see this is minus V reverse and here the current is I reverse current. The order is microamperes. So, now you let us recall for a normal PN junction in reverse bias, it was something like this, We try that we don't go in this region. That means we are here in this region. So, you see the current immediately becomes saturated. If this voltage is very small, then also the current will grow and become saturated. So, you see if I vary this, for increasing this bias, the current will become constant and this happens if this is I1. I1 is the intensity. Next, if I further for the same variation of this, if I increase intensity to I2, the curve will become I2. Then this is I3. So, here I3 is greater than I2 is greater than I1, where I is not the current, is the intensity of light. So, more light falls, more is the saturation current. So, here we must keep in mind that this reverse bias should not reach the breakdown region, otherwise this this photodiode will not work. If you want to work this photodiode in this region, then you have to suitably design it, and so the diode, this is the normal photodiode where the current is low and that is a saturation. Sometimes we require a special type of photodiode in which we want a current gain also. That means when the light falls, the current is very large, we want a current gain. That is a special purpose photodiode called avalanche type photodiode, which actually is reverse bias, so that the reverse biasing is at this stage. So, when the light falls, the current becomes sometimes here or so here the breakdown region is this, and so here current gain will be taking place. So, this is not our concern, but there are some special purpose photodiode that are avalanche type photodiodes, they work in this region. But normal photodiodes are designed to work in this region where the reverse voltage is less than the breakdown voltage. So, you see now next question let us tackle is why it is reverse biased, why not forward biased. You see here, when light falls in the depletion layer, then carrier generation takes place. As a result, this drift current increases. So, the order of drift current is in microamperes. Suppose when there is no bias, so or when light is, suppose 100 photons are falling, so the carrier injection, the carrier creation is, suppose quantum efficiency is 0.1, so only 10 electron hole pairs are created. So, the increment in the current is very small. So, but if it is forward bias, again the same thing will happen at the junction, but you see the order of current is in milliamperes. So, suppose a small increment takes place for a milliampere current, that won't be noticed, but a small change in microampere currents can be easily noticed. That is why when the change is easily noticed in a reverse bias. So, we can write this point as due to photons falling on the depletion layer, electron hole pairs are created, and so there is a increment in the drift current. So, there is an increment in the drift current. So, this increment is very small and can be noticed during reverse bias, but cannot be noticed during forward. Now, let us consider again this is our depletion layer and this is N type photodiode. Consider the portion of the depletion layer in N side of a photodiode. That means I am considering this shaded portion. So, what happens in the shaded portion? Let N and P be the number of charge carriers present there under no illumination condition. So, the N and P is the number of charge carriers. You see, the number of charge carriers will be generated by thermal motions also. So, let N and B be the number of charge carriers. Now, let N dash and P dash, let N dash and P dash be the number of charge carriers after illumination. So, when the light falls, then the number of carrier concentration is increased because of more and more carrier creation. So, N dash will be equal to previous N plus delta N. Suppose this is the number of charge carriers created by light due to photons. So, created by photons, and we have P dash is equal to P is the number of holes. So, will be P plus delta P. So, they are created due to photons, H nu light or simply photons. So, this delta P and delta N are created due to photons. So, now let us see this N type portion. This N type portion has a electrons as the majority charge carriers. So, this is very large compared to the holes. So, majority charge carriers N is there. So, N is very large compared to P. Now, this what is delta N and delta P? Delta N is the number of free electrons created by photonic absorption, and delta P is the number of holes created due to the same photonic absorption. So, whenever a photonic absorption takes place, then an electron hole, so delta N and delta P is created. So, delta N is equal to delta P. These two are same, you see these two are same, but N is very large. So, now if I take delta N, these two are same, delta N by N will be very less compared to delta P by P. Thus, this quantity is very large. Thus, we see that the change of the number of charge carriers is very large for minority charge carriers, i.e. here P holes. So, here you see that the change, the fractional change, this is denotes the fractional change. The fractional change is very large for minority charge carriers. Now, that is what we have discussed in the previous article, that why it should reverse bias. So, during reverse bias, the current conduction is due to the minority charge carrier, where a small change can be easily noticed. So, the photodiodes are always reverse connected. So, now let us come to light emitting diode, often called LED. A light emitting diode, which is often called LED, is a PN junction in which at proper forward biasing, at proper forward biasing, the spontaneous emission of light in visible spectrum takes place. Why it takes place? So, the majority charge carriers which diffuse towards the junction and recombine releases the energy which lies in visible spectrum. So, the band gap here is matches with the photonic energy. So, when in the depletion layer the holes migrating from the p side and from the inside the electrons, they unite, and so when they combine, the energy released lies in visible region and is emitted as the photon. So, this is what light emitting diode is. So, it should be properly biased. Generally, the biasing is different for different colors. So, this is a commercial LED light emitting diode. So, here you see, we see this whole thing. So, here this diode portion I am shading, this is the diode portion only, this is the diode portion. What I am shading is the PN junction only. This is the junction and this is P type and N type, and remaining you see this diode is very small, and one lead, this is metallized contact, and this goes to the positive terminal, and from this it goes to the negative terminal. So, this is the PN junction, this is N and this is P type. So, P is connected to positive and N to negative for forward biasing. And then this is the insulation, and you see this here the light emitted will, this design is such that the light emitted goes here, and this is a lens, epoxy lens, colored epoxy lens. So, it is red LED, white LED, blue LED, green LED. So, different colored LEDs are there, that colored lens will be there. So, finally, the ray will come out like this. So, this is the constructional details of an LED. Let us see its working diagram. So, now let us see its this point, concentrate on this point, this is of our interest, not this whole bulk. This is our now you see this is N type, you see this is the metallized contact. So, a contact, this part, this is the metallized contact, shade it, metallized contact. So, this is connected to this, suppose this is P type, so that we can connect this to the P type. So, there is a contact, metal contact. This is again N type, N type is here. So, this is N type, and here we have a contact like this, N type. You see, I am just drawing a cross sectional view. Actually, this is a whole, in the whole 3D it will be circular portion. So, we can, P is connected to this P type, N is connected to the N type. So, this is the what is here, this type of constructional details will be there. Now, let us see the working. Now, the VI characteristic of a LED is similar to the forward biased PN junction, but generally the threshold voltage is higher. Threshold voltage is higher for LED compared to the normal PN junction diode. However, the reverse breakdown voltages are very low, they are very low. So, care must be taken to limit the reverse voltage in an LED. So you see this is what happens. This is the threshold, this is the current in milliamperes, and this is the voltage. So then generally for silicon it is 0.7, for germanium 0.3 for a normal PN junction. But here the voltage will be high because normal PN junction has a forbidden gap of nearly 1.1 electron volt, but here the forbidden gap is somewhat larger, nearly 3 times larger. And here you see the reverse voltage is very less. So this is nearly 5 volts, the order of the 5 volts, the breakdown region, and this is several volts, maybe suppose 3-4 volts will be there, 5 volt, 10 volts will be there. So once not 5 volt, 10 volts, 2 volts, 3 volts. So generally it is the order of 2 volts, we can say 2 volts. That means once we give 3 volts, if we give a proper bias 3 volts, if I give 3 volts to that LED, then it will begin to come, begin to conduct, and the current will vary linearly with the voltage. It will be in the linear region. For low voltage edge, suppose 2 volts or 1.5 volts, the current is in this region. So its efficiency won't be very good. So we must give a proper bias, and we must not give this negative bias more. So for a normal diodes, it may be 20 volts, 70 volt, 40 volts, but for here it is the order of 5 to 6 volts. So reverse bias should be less for a LED, and forward bias should be somewhat more than the conventional PN junction diodes. So this is how it works. Now here there are band diagrams also we can show that this is the valence band, and these are conduction band, and there are some acceptor energy levels, donor energy levels. This is donor energy level, E acceptor. So let us see that how different transitions can cause radiative transitions and all this. First please copy this. Now you see here, this is the valence band. This is, suppose this is the valence band, and this is my conduction band. This is conduction band. We have here donor energy level, acceptor energy level. So generally what happens, the forbidden gap is somewhat lesser than the photonic energy. So what happens, a hole is created when a hole is there and this electron is there. So what happens, when at the junction the hole migrates and meets an electron, then an energy is released. The energy, this electron comes to this state. So the electron from the conduction band, that is from the n side, comes and joins the valence band hole, and then you see the energy is radiated. So this is a radiative combination. So you see, when this electron combines with this hole, then it is called a radiative combination. That means when this electron combines with the hole in the depletion layer, then that will emit a photon. So here a photon is emitted. There is many possibilities. So there is one more possibility, that suppose this electron here, and this is a hole, this is acceptor level, donor level, and this is the acceptor level, E acceptor. So this electron may come to this state, and then it may come to this state, means it may combine with a hole. This electron first reaches here and they may combine with this hole. So what happens, it radiates energy from here to here, and also it can radiate energy here to here. You see, when it comes here to here, it emits radiative, but only energy, this is lies in visible, this is non-radiative. You see, non-radiative means the energy will be radiated, no doubt, but that won't lie in the visible region. That may be in the infrared region, and that energy will be absorbed by the lattice. So it won't come out from the system. So this will come. This is the valence band, this is the donor level, this is your acceptor level. Now, you see the electron is here and it may directly come to this level, and so this also emits radiation. So, the electron available here may come to here, so in this process it won't emit. So, whenever it comes directly to this, or you see this to this, or directly from here, three possibilities are there. If it comes directly from here to here, it radiates. This to this also radiates, and this to this also. Suppose a hole is there, donor atomic hole is there. So, when it meets this hole, then it may radiate. Here this is non-radiative. That means what I have to, when I design, I keep in mind that this is slightly less than the photon energy, that is the light of that particular light which has to be emitted. Suppose red light has to be emitted. Suppose for red light the wavelength is our 0.7 micrometer and has an energy value of nearly 1.8 electron volt. For violet, nearly blue, this is at 0.4 micrometer and it has 3 electron volt. So, if I have to use a red LED, then the forbidden gap should be the order of 1.8 electron volt. So, EG should be somewhat less than, you can take it to be 1.7 to 1.8. Violet has a 0.4 micrometer wavelength and the corresponding energy of this is 3 electron volt. So, that forbidden gap should be of the order of 3 electron volt. This is how an LED works. So, now let us see what are the advantages of LED over conventional incandescent power lamps. So, number 1 point is they have low operational cost. That means the electricity usage is come. So, in order to operate these LED, the power consumption is very low, whereas in conventional lamps the power consumption is very high because that power is directly converted into heat. So, majority of the energy is converted into heat. So, they have low operational cost, and so they consume, because they consume less power. So, why they have low operational cost? Because they consume less power. Second, they are fast and does not take much time in switching or warming. So, their switch on and off is, they have long life, they have very long life and ruggedness. So, their life is very large compared to incandescent bulb where there is a filament, it breaks up, but this is solid state device, it has a very large lifetime. Then the light emitted by LEDs are highly monochromatic. I want red light means it will give a very highly monochromatic, that means the red light only will be given, but incandescent bulb will give a lot of wavelength spectrum from red to yellow like that. But this will, if I say it's green LED, means the wavelength will be very precise, the variation of wavelengths will be, the bandwidth of the variation will be very small. That means it is highly monochromatic. So, they are less operational cost, they are very fast, they have very long life and the energy is highly monochromatic. So, these are the advantages of LED over the conventional power lamps. Now, let us see what are solar cell. They are often called photovoltaic cell. So, they are PN junctions similar to the photodiodes similar to photodiodes. You see, photodiodes are used to detect light and it is always reverse biased. So, this is not reverse biased. In fact, there is no biasing in the solar cell. So, they are PN junctions similar to photodiodes which are used to convert solar energy or light energy into electrical one. So, the basic between a photodiode and a solar cell, the material may be same, the physics may be same, but constructional details will be different. So, here we have to collect the solar energy and convert it to electrical one. The depletion layer here has a very large surface area. So, the depletion layer has a very large surface area so as to collect as many as electron hole pair possible. So, we have to collect as many as electron hole pairs possible. There is no biasing because we have to collect the electron hole pairs, the electrons to the N side and holes to the P side, and when they are connected, then they supply the electric current. Now, let us see the constructional details of a photovoltaic cell, solar cell. So, here this is a PN junction, this is a block, this is in the form of a sheet, this is very small, this thickness is very small, this surface area is very large. This is P type. So, the bottom of the P side is here metallized. So, this is metallized contacts. So, this side a metal is deposited, a metal area on the whole area it is deposited. So, this is for a contact, and here you see this shaded one I am shading is a metal, this is the metallic contact here, and these are fingers, these are lines. So, these are the metallized contacts, metallized fingers. Fingers means they are just printed fine wires like this. You see, and this is its cross sectional view. This is the metallic contact with the P side, and you see these are the fingers I have shown. These are the fingers shown, and this is N type. Now, if light has to fall on the junction, you see this is the junction. When I represent this by a block diagram, I represent that this is the junction and light falls. Actually, light can't fall like this. This thickness is very small. So, this junction is actually here, you see in this diagram. This is the junction. Now, what happens? This inside there is a limitation for us. This inside must be transparent. So, transparent, so light falling through here must enter and reach this region. So, light falls through here and must reach it. That is why in order to connect to inside, we have just kept here fingers. We have not kept this whole metallized, otherwise light won't reach the junction. So, here we have to keep in mind while designing this material N should be first of all N type semiconductor, and it should be transparent medium because the light has to come. So, that is why the choice of n has a very limited range. Number one point is this, the forbidden gap for this should match with the light which has to be captured. So you see here, if this is violet and you see this is our red light, then the energy, this is the energy what we receive. This is, our eye is sensitive in this region. Now suppose we have to design this solar cell to capture sunlight. So sunlight maximum energy is in this region, sunlight visible region. If I have to use another light, suppose this light which is in our classroom, then this light is not similar to sunlight, it is near to violet region. That means we have to design this our forbidden gap in such a way that these are the donor energy levels and these are the acceptor. So there are a wide range of energy band available from this to this, so as to capture all types of photons in the visible range and then cause an electron hole pair, and then they constitute the EMF between these two. So the constructional details should be such that this N should be transparent, its absorption coefficient should be very less, so that the photons can reach the depletion layer and can cause this electron hole pair, and thus further EMF formation will take place. The area, you see this area is kept very large. So the design is here such that to make this area very large, whereas in the photo diodes this type of arrangement is not done. So now let us come to see the mechanism of the generation of EMF of a solar cell. So mechanism of EMF generation. So now the process of EMF generation in a solar cell involves the three steps. Number one, carrier generation. Number two, carrier separation, and number three, charge collection. So first generation, then separation, then collection. Generation, separation, collection. So let us come to the first, carrier generation. So when light of appropriate energy falls on the junction, then it creates an electron hole pair. The point is Eg is somewhat greater than Eg. So the light energy is somewhat greater than Eg. So thus an electron hole pair is created. Next, the generated carrier, the generated electron hole pair is separated by the junction field, by the high junction field, so that the electrons go N side and holes P side. You see, the doping level is very high, so that the junction voltage is high and there are a lot of options. The doping level is so high, so that the electron hole pair can be created more and more. So, now the third step is the charge collector. The electron reaching N side is collected at the contact, at the metallic contact, and the holes to the metallic contact at P side. When they are externally connected, then the electrons from N side flows through the wires and meet the holes at P side. So, now come to the VI characteristics of a solar cell. VI characteristic of a solar cell. Now, you see, the VI characteristic of a solar cell lies in the fourth quadrant. Why? Because it does not withdraw current but supplies current. So, you see, it does not withdraw current, it supplies current. So, you see, this is my plot I am going to do here, and this is the current and this is my voltage. So, my graph should be actually something like this, and then it's something like this. So, reverse. So, this quantity is very small, so just show it to be here like this. So, this is the VI characteristics where when it is dark. So, if my solar cell, if you draw the solar cell VI characteristic of a solar cell in dark, we will get this curve. It works like a normal p-n junction, but actually when we illuminate it, this is the graph, this graph something goes like this. So, this graphs, this is under the condition of illumination. So, when you illuminate, when you put light, then this graph of the solar cell will be for dark condition where it behaves as a normal p-n junction. It works. This is VOC and this is IOC, that is open circuit. So, first draw it. So, here VOC is open circuit voltage, that means the EMF generated when the solar cell, suppose this is my solar cell and when this is open. So, when this is open, now when you connect it, then the voltage will drop, and ISC is short circuit current. So, you see, when this is open, when this is open, this voltage will be VOC, and when this PN junction is connected by a short circuit, then the current ISC, and when we are using a solar cell, this is PN junction solar cell. So, we connect a load and we are using this, so the current is IL. So, when you are using IL current and the power output you will get across the load resistor, when this is short circuited, the current is ISC, you get this current. When it is open, the voltage is this, and the graph is something like this. So, this is similar graph, something like this. This is the VI characteristic of a solar cell. So, thus we have seen all the three basic type of this optoelectronic device, and in next class we will see another junction device which is called a Zener diode.